Hi, welcome to discussion 3. This week we have covered sampling and reconstruction. So in the lectures, we learn the concepts, and in the discussion, we'll dive into exercises to have a better understanding of the calculation behind it. All right, so let's come to problem 1. So the problem 1 describes a data flow. So we have xt, a known x s of t, and then it is multiplied by y of t, and we know what is the Fourier transform of y of t, and then the result is called z of t. Z of t will go through an AD converter, and therefore it becomes z of n, right? And then we'll put z of n into a low pass filter, and then we get our outcome out of them. All right. So in the lecture, professor mentioned that there will not be an ideal band limited filter. But in the exercise, we'll assume that the energy out of the band of interest is low enough to ignore. So let's get comfortable with this. So the question 1 is, we know that the big X of big F looks like this. So it is nothing but a window range from minus F1 to F1, okay, with magnitude 1. Similar for Y of big F, and the relationship between F1 and F2 is this. F2 is half of the F1. Okay, so the question is, what is the Nyquist rate for Z of t? We know that Z of t equals to X of t times Y of t in time domain. All right. So or our information as their waveform in the frequency domain, right? So we'd like to convert it into frequency domain. What's wrong with this equation?
Multiplication times convolution.
Exactly. Yes. So usually we turn the convolution in time domain into multiplication in frequency domain, but don't forget that vice versa. So in this case, it is convolution in frequency domain. All right. And to get the Nyquist rate, we know that the Nyquist rate is 2 times of the let's say the band, right? So to get intuition, we'd better draw the plot of z of f to get an idea what should be the b. Agree? All right. So this is basically the convolution. Let's say it's similar to the convolution in continuous time domain, right? Because it is not time domain, but they are continuous. So it will remind you something in the 102, and we flip the y of f and to slide it from the left to right until they overlapped, right? So the common area is 0 here, and then it increases gradually until they fully overlap, right? And when they fully overlap, we can say the convolution value will reach its maximum, and then it remains on that level until the small window begins to leave the big window, and then the common area decreases until 0, right? So the waveform of big F should look like something this. We increase and then maintain the level and then decrease, right? It should be even symmetric. But we also want to know the exact value, right? So let's go back to the intuition. When they first have a little overlap, the index should be minus F1 plus F2. And when they fully overlap, it should be minus F1 plus F2. For this, when it starts to leave, it is F1 minus F2. And when it fully leaves the window, it should be F1 plus F2. So you see that they're even. It is even. Okay. So now you can see that we get B equals to F1 plus F2, right? So we are not talking the band pass sampling and reconstruction. So here you see that the spectrum is centered at DC, right? At F equals to 0. So we just basically apply it and sample it with FS. So it is, and record the relationship between F2 and F1. It is equal to 3f1. Okay. Any questions up to now? All right. I hope it is easy to follow. And then let's come to sub-question B. So in the previous data flow, we noticed that the A to D converter has a sampling rate of fs. So let's give a concrete number of fs. Let's suppose fs equal to 4f1. Okay, and you see that it meets the Nyquist rate, right? And my question is, let's plot the DTFT of out of n. What is out of n? Out of n is the output after Z goes through the ideal low-pass filter. All right. So to solve for L of n, we first need to let's talk about the way of thinking. We first need to plot the DTFT of Z of n, right? And then we apply the low-pass filter, whose spectrum is drawn here. We'll get the DTFT of L of n. All right. For convenience, let me paste it here. All right. Great. Okay. So record the equations of DTFT. Well, we don't need to do the calculation of this because we don't know the expression of Z of n. We can know it, but we don't need to calculate it at this moment. We just need to do some observation and transfer the Z of big F into our Z of omega of interest. Okay. So our question becomes this. And in the lectures, the professor mentioned, so when you sampled it in time domain, it becomes periodic in frequency domain, right? So from ZT to Zn, we are sampling it in time domain. And correspondingly, the frequency domain should repeat. So we will have some other spectrums like this. When we let's say when we it is semi DTFT. I said so because we have not transferred the F into our omega, right? So for DTFT, we know that the spectrum is periodic on omega. So usually we only take its baseband, which is minus pi to pi, right? And professor mentioned that this is what MATLAB do. When you plot DTFT, it only gives you the result between minus pi to pi because it's always repeating. Yes. So let's forget about the sideband. Okay. So the problem becomes how to transfer F to omega. So F is a frequency in continuous time domain, and the omega is a frequency in discrete time. In discrete time domain. So omega equals to 2 pi f, and f is also in discrete time domain, and the f is equal to f over fs. So we'll get the equation like this. Okay, continuous time, and this is basically the sampling frequency. All right, so it becomes clear, and our originally b, which equals to f1 plus f2, now it should becomes 2 pi f1 plus f2 over fs, right? And then we know fs equals to 4 f1, and this, the numerator is this, and we'll get our, no, it is not this, 1.5 f1, all right? We'll see it is, well, 3/4 pi in omega. So similarly, we can get other time indexes. And after some calculation, we got a range from minus 3 over 4 pi to positive 3 over 4 pi. And similarly, we get the turning point is 1/4 of pi. All right. And then what about its value? So let's go back to the Z of big F. When they fully overlap, the common area should be the area of Y of F, right? Because it is fully included in the window of X of F. Okay, so the area of this is 2F2, right? Because the height is 1. So we can say that is as high as 2f2. Okay, and we know that when we do the DTFT, the value will drop. No, it's not drop. I would say it will times. Oh, sorry, it's f2. The original value will times fs. So, like in the lecture notes, it is proved, right? So when we try to put the excess big F into a formal DTFT, we'll see that the 1 becomes fs. Okay. So similarly, the 2f2 becomes 2f2 times fs, and it is equal to 4f1 squared, given f2 equals to half of f1. Is it? Yeah. And fs equal to 4f1. Wow. Okay. Any problem up to now? Great.
Wait, wasn't FS
Hmm?
3F1?
Sorry?
Wasn't FS 3F1 instead of 4F1? Or is this problem different?
You mean here?
Yeah.
Oh, sorry. So in question 1, we are calculating the Nyquist rate.
Yeah.
Yeah. So yeah, thanks for
Okay,
reminding. I will change it to another
yeah.
notation. So the Nyquist rate. Thank you so much. So it is not confusing now. Great. Okay, so we are almost done in problem B. So our last step is let the z of omega go through the low-pass filter, and get L of omega, right? So we mentioned that the low-pass filter is an ideal window from the minus pi over 4 to pi over 4. And this will be very easy here. So we're basically cutting the sides out, or the things out of the window. And what we get is, so the value is 4 f1 squared, and the range is the range of the filter. Clear? Nice. So we are done. But in reality, maybe we are interested in turning the out of n into L of t. So we have a D two-way converter, and then let's say the fs is due for f1. Let's get L of t and see its relationship with x of t. So to turn it back into the time continuous time domain, we simply just need to do the converse. So if you remember, we times an fs when we want to convert it into DTFT. So we need to divide it by fs this time to get our original level. So the L of f, the level will become f1, given fs is 4f1. Okay, and then we need to convert the horizontal axis back to f1, and we still use that equation, but this time we need to move all the things on the right. Okay, and this time we'll get half of f1 minus half of f1 here. All right, so if we want to relate L of big F to our original L of x of big F, we'll see that the level, so their shape are the same, right? But the level from 1 change from 1 to f1. So change from 1 to f1, and the window size also shrink, right? Shrink by a factor of 2. So this is actually x of 2f. So this is our observation. Nice. We are done with problem 1. Any question?
Wait, hold up. Could you go over the relation between L of f and x of f again? Or that. Like how you said,
Sure.
Yeah.
So it is more like a observation instead of calculation. And let's compare these two spectrum. You see that they have the same shape, right? But the size of the window is different, and the height of window is also different. So we use the f1 to indicate the change of height from 1 to f1. And we add a 2 here, 2 of f, to indicate that the window shrinked by a factor of 2. Does it make sense?
I see. Yeah. Thank you.
Great. So hopefully this question will help you understand the xs of f between this and our DTFT. Okay.
Why did we convert to omega and then back to f?
Because the f. Oh, why? Okay. Because I add a component to the original data flow, and I say if we want to convert the out of n back into out of t, which is in continuous time domain, what will happen? So this is an extra question I ask.
And then
put it here.
Just in general, like even when we did the original DTFT, why don't we just keep it in terms of like little f instead of omega?
Sure. You can use this f, no problem. But I change it to the small omega because the low pass filter is expressed in this way, so it would be more convenient for us to do the calculation between LPF and z of n.
Okay, thank you.
You're welcome. Great. Thank you for your question. You follow very well. And let's come to problem 2. So we won't use so much time as last time, so I will be careful about it. Thank you for your patience. In problem 2, we also have a data flow. But this time we'll do the trick of shifting the signal. All right. And so we also start with a continuous time signal, and you directly come into our A to D converter. And we know that the Fs equals to 10 Hertz, right? So this time we use a specific number because you guys has become more familiar with it. And then, it will become x of n, right? And then let's come to a system that we know the impulse response. So the impulse response is j omega over t, where the omega is limited into this range because we know it's periodic in frequency. And then we'll get y of n out of the box. The y of n would like to go through a t to a converter, and then becomes a continuous time signal again. All right? And let's say you have the same frequency. Great. Okay, so maybe some of you already start to think about how will it look like after go through the H box. So let me give you some more concrete number. Let's say we already know xa of t equals to cosine 6 pi t. And yes, my question is, tell me what is ya of t? Okay. So it seems like a long way to get ya of t, but it won't be that scary if we break it down into blocks. All right. And to save you from computation, let's recall our professor said about like converting the cosine into the frequency domain. So I hopefully you guys remember that cosine omega t will maps to, this is f, this is 0, will maps to 2 impulse. So if it is a here, the height should be half of a, and this here. All right. So I'm not going to explain how we get this. Let's just use the conclusion. So for our xa of t, what will we have? Let's say it is big X of big F. The magnitude is 1. So in the frequency domain, it should be 1/2. All right. And the index of F is -3 and 3 because we have 6 pi here, right? Great. And so we are representing this with in frequency domain. Now we sample it with 10 Hertz. And I hope you guys remember when we sample on it, it would become periodic in frequency domain, right? So when the sampling rate is high, the periodic will be long, like this, and repeating without alias. Okay. So here we can get a very concrete result. We know that fs equal to 10, so it is shifting with amount of 10. It is 0 here, so it should be 10 here, and plus 3, so we have 13, 7, all right? And we have minus 10, and then minus 7, an impulse here, and minus 13, an impulse here, right? So as we mentioned before, if we want to turn it into the omega, let's say even we don't want to turn it into omega, we still need to change the magnitude by times it with fs, right? So or the half will become half of fs. And we know that if we want to convert it into omega, we have to do this calculation. And fs is 10, so it becomes this, right? And for example, the 13 here should be 13/5 times f. All right. And recall the Nyquist rate. If we're sampling at fs, we would like to get the window of half of fs from negative to positive, right? And here it should be -5 to 5. And let's see where is the range. All right. So the range is here. We only want to get this for x of omega because we know it is repeating. All right. The reason why we draw the sideband here is because if they have alias or if they have any other situation, we can also cover it. Like, yeah, but here we don't have alias, and what we get is very clean and lovely. So I would say this is x of omega. This is not really a x of omega in the previous plot because you're still showing it in big F and you're still showing all the rest repeating spectrum. Okay, but this part is necessary to prevent you from making mistake. So this is half of fs, and our previous range of the baseband will become pi and minus pi now, okay, in omega. And then similarly, we'll have 3/5 pi minus 3/5 pi. All right, we are one step closer to our result. And the next step can be predicted by you guys. So we have h of omega and we have x of omega, right? And you know that it is convolution in the time domain, the discrete time domain. So we just need to multiply it in the omega domain. And the condition is very convenient for us. So we know that omega, y of omega equals to x of omega times h of omega. Okay. And the h of omega is j omega over t. And the x omega is 2 impulse function. So the y, it's clear that the y is also the impulse, but the magnitude is time with this, right? Yeah, so the t here is 1 over fs. Let's say it is given by the question. All right, the horizontal axis remain unchanged, and the vertical change to, let's say we have a, we can include the complex here, complex number here. So we know the value is, all right. And the omega here is, let me see if I make any mistake. Okay. The T. Okay, no mistake. All right. Well, I'm not confident at my calculation. Sorry. Great. Yeah. So what can we do right now? So now we need to convert the y of omega back into the time domain, right? So we need to make it in time domain, continuous time domain, sorry. And as you remember, we times the fs here, and then we need to divide it by fs again. So it becomes the j 30 pi will now becomes j 3 pi. Yes. Oh, I see where I made a mistake. No wonder I'm so unconfident. Okay, so on the left side, the omega is minus 3/5 pi. So in the equation, it will be negative. So it should be minus j 30 pi. Okay, no problem now. And let's convert it into continuous time domain again. All right, and we know that omega ts, this is continuous time, this is discrete time. Okay, this is a conversion, the relationship. So the value will become minus j 3 pi and j 3 pi. And the index here should becomes time fs, which equals to 6 pi, and this is minus 6 pi. Is it clear? And then record this DTFT, CTFT of sine function. You see that the format will match. So if we write it down, so y of omega equals to j 3 pi times an impulse at 6 pi, and then minus an impulse at minus 6 pi. All right. And if we turn it back to f to observe it better, we'll have j 3 pi sigma f minus 3 and minus f plus 3 here. Okay. And then you see that it is actually the CDFT of this function. Okay. If you can directly observe it from the big omega format, it is also fine. So this step is not necessary, and just for a cleaner observation. Okay, so now you see that the y of t equals to a sine function. So we are done. We already get ya of t. And for fun, let's observe the relationship between x of t and the y of t. So can you observe?
So to convert y of omega to y of f, what exactly is the process there?
Sure.
Yeah.
So the big omega is the frequency in rad per seconds. No. So the omega is a frequency in continuous time domain, and the big F is also the frequency in continuous time domain. And their relationship is just this.
Right. So I guess yeah. Mm-hmm. Yeah, no, I was curious, like, why does the delay also get divided by 2 pi? Or, well, yeah, like, for example, like the magnitude in front doesn't get divided by 2 pi, but the delay does. Is that just because they're like inputs to a function like delta? That's why they get scaled? Or
okay. So I guess if you observe this plot, is there a 1/2 pi relationship there? I
guess I see. It's since you're just pulling it from the graph. So since the amplitude stays the same, but I guess the delta positions change. So you just directly create the equation from the graph. I guess I get that.
Yes, that is what I did. So if you're doing the equations of CDFT, and you can feel free to change your variable from the omega to f, and it will not change your magnitude. The only difference is when you try to recover the y of t in terms of like something times the big Y of omega or the Y of f. In this case, it would generate a multiple about the about 2 pi. So switching between the y of f and omega, it is fine because it is only changing the horizontal axis. Okay. So let's see the relationship between the y of t and the x of t. What can you learn from it?
The frequency is the same, but it had like a, I guess, a phase shift in a magnitude change.
Yes, almost there. So their frequency are the same. And if we take a closer look at it, we'll see that the 6 pi goes to the amplitude. And it is basically the differential relationship. So the y of t is basically the derivative of x of t, right? So back to our data flow. This is basically a differentiator. All right, so that's a bonus of this question. So that is the end of today's discussion. I hope you guys learned something from it, and I will be back in 10 minutes and start the office hour. Thank you.
Thank you.
Thank you.
Thank you guys for great questions as well.